I want you to step into a physical space with me for a moment. Just imagine you're walking onto the floor of a massive state-of-the-art manufacturing facility.
A place completely dominated by very specific industrial noise.
Yeah, it's an ocean of noise, but it is a highly orchestrated kind of noise. You can hear that low, continuous hum of heavy servo motors driving the main line.
The rhythmic metallic clack of conveyor bearings turning over and over.
Right, and maybe down at the far end of the central aisle, you catch the polite, distant beep of a forklift reversing, just moving materials around.
So you are standing right in the middle of this physical space.
And you are witnessing the immediate aftermath of a massive, multi-million-dollar operational improvement project. It has just officially wrapped up.
And if you look around, by every conventional measure, this project is a triumph.
Absolutely, because if you look up at the walls suspended above the production lines, there are these massive digital dashboards.
And they're all glowing a very healthy, vibrant green.
Right. The local cycle times for the individual machines are demonstrably down. The efficiency metrics are just climbing the charts.
You can probably see the management team in a glass-walled conference room overlooking the floor.
Yeah, they are in there actively celebrating a major win. They're armed with these pristine slide decks showing arrows pointing enthusiastically upwards.
It looks like a picture-perfect moment of industrial progress.
It does, but let's unpack this. Because there is a single incredibly awkward detail that completely shatters this illusion of progress.
Even if nobody in that glass conference room has actually realized it yet.
Right. If you turn away from the dashboards and you walk down to the shipping bay and you physically count the boxes being loaded onto the trucks,
You will find that finished goods are leaving this building at exactly the same rate as they were yesterday.
not a single extra unit has been shipped.
What actually improved?
And that question right there, that is what ruins the celebration.
It's that uncomfortable realization that a system can move significantly faster while getting absolutely nowhere.
Which is the foundation of our entire deep dive today. We are exploring a remarkable document called the Field Notes Research Operating System.
Specifically, the FNROS version 2.0 dossier.
Yeah. It is this dense, thoughtful collection of engineering essays and visual concepts. And all of it is gathered under a very provocative title.
When AI optimizes the wrong constraint.
So our mission for this deep dive is to build a permanent mental model for you. A framework for understanding optimization and systems thinking.
And why highly intelligent systems, specifically the artificial intelligence tools flooding into our workplaces right now, often fail.
And they fail for surprisingly unintelligent reasons. Usually because humans have a habit of choosing the wrong objective.
But I do think we need to push back a little right at the start.
Sure, because we have been conditioned to view speed through a very specific lens.
Right. Usually when we talk about AI, it's framed as this absolute magic wand for productivity. It makes everything faster and removes friction.
And historically, we've been taught that speed is inherently good. I mean, if a system is producing the same amount of value, but the internal gears are suddenly spinning twice as fast, doesn't that matter?
You would assume that faster eventually equates to better, even if we haven't seen the results hit the shipping bay yet.
It's a very natural assumption to make, particularly because our modern work culture is basically built on the legacy of early 20th century scientific management.
We were taught by industrial engineering pioneers that if you optimize the individual worker's speed, the factory naturally produces more.
But that assumption is one that modern engineering history repeatedly proves wrong.
Which brings us to the core editorial question that will anchor our entire conversation today.
The lens through which we need to view every green dashboard and every new AI tool deployed in your organization.
If this process became 10 times faster tomorrow, would the system actually improve?
10 times faster, an order of magnitude improvement in speed. But the system itself doesn't improve.
I hadn't connected those ideas so starkly before I spent time analyzing these heavy manufacturing environments.
Right. Looking at the physical reality of it changes how you think about optimization entirely.
We assume that if a localized part of the system accelerates the global system, naturally benefits, that the time saved just sort of cascades downward.
But the reality of physics and the mathematics of queuing theory are much less forgiving.
A faster gear in the wrong place doesn't pull the system forward. It simply grinds down the teeth of the gear next to it.
Let's shift the environment for a second to ground this in what most people are experiencing right now.
Moving away from the physical factory and into the digital realm.
Yeah, I want you to imagine the quiet, rhythmic, rapid clicking of a mechanical office keyboard. Maybe the faint notification chimes of a messaging app.
Because there's a massive glaring contradiction dominating our news feeds today.
If you look at business media, the narrative is that AI is performing miracles of acceleration.
It writes complex Python code in seconds. It drafts airtight 50-page legal contracts.
It generates quarterly reports. It can listen to a chaotic hour-long strategy meeting and summarize it into 3 actionable bullet points before you even stand up from your desk.
Judging by the capabilities being advertised, every knowledge worker should be working a 2-hour day right now.
We should all have enough free time to learn a new language or just stare at the ceiling.
But instead, what is the lived reality of the modern professional?
People just have more emails. We have more meetings to discuss the summaries of the previous meetings.
The technology is doing what it promised to do. It is accelerating the tasks.
But the human experience of the work and the overall output of the organizations hasn't actually improved.
That explains something I've seen developing for years. But the current generative AI landscape has just amplified it to a breaking point.
We are collectively confusing 2 fundamentally different concepts.
Right, we are confusing acceleration with progress.
Acceleration is a property of a task. Progress is a property of a system.
You can accelerate a localized task to near light speed. You can reduce the time it takes to write an email from 10 minutes to 10 seconds.
But if that task isn't the specific thing holding the entire system back, you haven't made progress.
You've just created a lot of very fast, very impressive motion. You increase the kinetic energy of the system without changing its trajectory.
It's just motion dressed up as progress.
That is a very accurate way to describe it. And this brings us to the greatest strength of artificial intelligence, which, paradoxically, is its most catastrophic flaw.
It is wonderfully, perfectly obedient.
It is a tireless optimization engine. It optimizes faithfully based on the objective function it receives.
But it has absolutely no opinion on whether the objective you handed it deserves to be optimized in the first place.
It completely lacks the capacity for systemic doubt.
The dossier captures this dynamic so well. It points out that AI is so enthusiastic about its programmed objective
That it will happily schedule another meeting to discuss the emails about the previous meeting.
Yeah, it will flawlessly optimize that massive convoluted legacy spreadsheet that everyone in the office secretly hoped would just quietly disappear.
It doesn't judge the utility of the work, it simply executes the work.
We continually frame this as a technology problem or an AI alignment problem.
But looking closely at the dossier, it becomes clear this is fundamentally an engineering problem. We are misapplying the tool.
To borrow an analogy from the notes, we are essentially handing a set of meticulously engineered Formula One racing tires to a parked car.
Artificial intelligence fundamentally changes the cost of execution. It drives the marginal cost of generating text or code down to near zero.
It makes doing the thing incredibly cheap and fast, but it does not and cannot choose the destination.
But let me play devil's advocate here because the individual incentive is very strong.
Sure. Isn't optimizing a small, localized task inherently good on an individual level?
Let's say I use an AI tool and it legitimately saves me an hour a day answering routine client emails.
I get that hour back. My inbox is at 0. Isn't that a win? Even if I am a parked car, at least my tires look great.
On a purely individual level, it absolutely feels like a win. You experience a reduction in cognitive friction.
But organizations and the systems that drive them do not operate on individual feelings of productivity?
Right, they operate on flow.
Yeah.
They operate on the continuous movement of value from conception to the customer.
If you save an hour on emails, but the core function of your job, let's say approving a new product design, is still waiting on someone else's input.
Or waiting on a legal review. What have you actually achieved for the organization?
You have optimized what is visible. Your inbox is empty. But you haven't optimized what is limiting.
When we optimize the visible rather than the limiting, we simply create a faster version of the wrong thing.
We become exceptionally, blisteringly efficient at waiting.
Okay, we are throwing around some heavy engineering concepts here, and the FNROS dossier is absolutely packed with them.
The text demands that we don't just use these words as buzzwords, but that we actually understand the physics behind them.
Before we go any further down this path, we should establish some absolute first principles.
Yeah, I want to break these terms down because they are the load-bearing pillars of this mental model.
We need to thoroughly unpack optimization constraints, throughput, local versus global optimization, and queuing theory.
Let's start at the bedrock. Where do we begin?
We have to start with the theory of constraints. This is a management philosophy introduced back in 1984.
It was born in the era of heavy manufacturing, but it has never been more vital than it is right now in the age of digital acceleration.
The core premise is brilliant in its simplicity, but incredibly difficult to accept in practice.
Every system, no matter how complex, possesses exactly one constraint at any given moment. One single bottleneck.
Everything else in that system, all the other machines and departments, exist solely to support that constraint.
Just one. I can imagine a listener saying, you don't understand my company. Everything is broken. We have 50 bottlenecks.
But the theory states there is always mathematically just one.
Think of it like a chain. A chain can have many weak links.
But when you pull it until it breaks, it only snaps at the single weakest link.
At any exact millisecond in time, there is one limiting factor that dictates the maximum speed of the entire system.
If you improve that specific constraint, the throughput of the entire system improves.
But here is the trap, and this is where the vast majority of AI optimization efforts go to die.
If you improve literally anything else in the system that is not the constraint, the system does not improve.
If you take a link that can hold 100 pounds and spend $1 million using AI to upgrade it to hold 1,000 pounds.
But the weakest link can still only hold 50 pounds. The chain still breaks at 50 pounds.
You haven't increased throughput. You have simply increased the cost and localized efficiency of a non-constraint.
That perfectly sets up an analogy from the dossier, which takes this abstract idea of links and makes it undeniably concrete.
I want to spend some time on this because it physically illustrates the concept of local versus global optimization better than anything else.
Imagine a massive motorway, a major highway with 6 wide, sprawling lanes of traffic moving along at the speed limit.
But a few miles ahead, due to a major infrastructure project, those 6 lanes are forced to merge into just one single lane.
Anyone who commutes has lived this specific nightmare. The brake lights stretching into the distance.
So look at that system through the lens of local optimization. What happens if the local city council decides to widen the first part of the highway?
What if they expand those 6 lanes to 10 lanes or even 20 lanes and let those ultra-wide lanes run indefinitely right up until the merge?
If we look at the physics of traffic flow, the answer is brutal. Traffic still stops at exactly the same geographical location.
Adding 100 miles of perfectly empty, ultra-wide motorway right before a single-lane merge does absolutely nothing to increase the throughput of cars exiting the zone.
Let's look at the mathematics of it. If the single lane can only process 1,000 cars per hour, that is your constraint.
That is your system throughput. It does not matter if 5,000 cars per hour are arriving via the 20 lanes.
Or if 1,500 cars per hour are arriving via 2 lanes. The output remains 1,000 cars per hour.
Widening the upstream lanes is local optimization. It improves the metric of lane capacity in a vacuum.
But it actively harms the global optimization. In traffic engineering, widening those lanes often makes the bottleneck worse.
Because it increases the turbulence and friction at the point of the merge.
It seems so wildly obvious when you picture the asphalt and the cars. No rational person would build a 20-lane highway that abruptly turns into a dirt road.
Yet the dossier points out that massive sophisticated organizations make this exact multi-million-dollar architectural mistake every single day.
With their enterprise software and their human capital?
They do it constantly. And they do it because in a digital business, the lanes aren't made of concrete.
And the cars aren't visible physical objects. The lanes are software capabilities or server capacities.
The cars are data packets or lines of code. Organizations optimize what they can easily measure on a dashboard.
They widen the digital lanes because widening lanes feels like progress. It looks like aggressive action.
Which brings us to queuing theory. Because when those invisible cars hit that invisible merge, they don't just disappear.
They form a queue, and the way the dossier characterizes this dynamic is brilliant. It almost gives the bottleneck a personality.
It observes that bottlenecks have this remarkable quiet patience. They don't scream for attention or set off alarms.
They just quietly, steadily collect work. They build up queues of inventory.
And most importantly, the bottleneck never, ever attends the meeting where everyone discusses improving everything except the bottleneck.
That observation is incredibly sharp. Constraints trick human intuition.
Because the work piles up before the constraint, it creates a massive visual backlog.
It creates waiting and starvation downstream, but it convinces everyone looking at the system that the problem must be upstream.
If you are standing at that one-lane merge and you look backward in a 5-mile-long traffic jam,
Your immediate human instinct is to say, wow, we have a massive traffic volume problem back there. We need more lanes.
you misidentify the symptom. The cue is the root cause. You try to solve a constraint problem with an acceleration solution.
This is where we need to take these first principles out of the textbook and into the real world.
The dossier provides these incredibly detailed, cross-disciplinary industrial vignettes to prove this is a universal physics problem.
Let's walk through them and go deep into the mechanics of each one, starting back in the physical world, manufacturing.
I want you to imagine the smell of aerosolized machine oil, the heat of the metal, and the deafening sound of heavy stamping presses.
In this scenario, the plant management has recognized they need to improve efficiency, so they invest heavily in an AI-driven production scheduling software.
It is a marvel of localized optimization. It ingests thousands of variables.
Raw material delivery times worker shift schedules, tool changeover times energy costs.
It calculates the absolute mathematically flawless order of operations down to the millisecond.
The schedule it produces is a work of art. From a purely computational standpoint, it's a masterpiece.
The AI is doing exactly what it was asked to do: minimize idle time on the schedule.
But here is the physical reality check that the algorithm cannot perceive.
The preventive maintenance team in this factory is understaffed by 3 people due to budget cuts last quarter.
Because they are understaffed, routine maintenance, like lubricating bearings or replacing worn seals, is delayed.
And because routine maintenance is delayed, the primary stamping press, the absolute heart of the production line, overheats.
It physically breaks down for 4 hours every Tuesday afternoon.
I hadn't connected those ideas before, but looking at it as a system, suddenly that multi-million-dollar AI software is completely irrelevant.
It's worse than irrelevant. It becomes a source of chaos.
The most elegant, highly optimized AI schedule is completely useless if the machine physically cannot run.
The software accelerated the planning phase. It removed all the friction from deciding what to do.
But it entirely ignored the physical constraint of the maintenance capacity. The system didn't improve.
In fact, because the AI scheduled the machines to run tighter with less buffer time, the inevitable breakdown causes a much more catastrophic ripple effect.
They accelerated the system right into a brick wall.
Let's take that exact same failure mode and apply it to a completely different environment, healthcare.
We're in a major regional hospital network. The administration is trying to reduce physician burnout and improve patient throughput.
They deploy a state-of-the-art AI medical scribe system. The mechanism is incredible.
The doctors simply talk naturally during the patient consultation. The AI listens, processes the medical terminology, and automates the clinical documentation.
It generates the SOAP notes, codes the billing, and updates the electronic health record instantaneously.
The doctors are finishing their charts in record time. Their personal efficiency metrics are off the charts.
They are leaving work an hour earlier, and again, this is a brilliant application of technology for a specific localized task.
The doctor's cognitive load is reduced, which is objectively good. But let's look at the patient's journey as a complete system.
What is the actual physical constraint in patient healing in this specific hospital network?
When we map the flow, we discover that patients who present with complex neurological symptoms are still waiting 3 to 4 weeks.
Waiting to get a scan on the only MRI machine in the building. The imaging department is the true constraint.
So the doctor dictates the clinical note 10 times faster. They conclude in seconds rather than minutes that the patient needs an MRI.
The AI instantly generates the referral. The activity increased. The speed of the documentation increased.
But what happened to the throughput of patient healing? It just shrugged.
The patient still waits 3 weeks for the scan. The overall system timeline for that patient's diagnosis and recovery didn't shrink by a single day.
The hospital invested massive capital in AI documentation, but they didn't point it at the MRI backlog.
They didn't use AI to optimize scan times or simply buy a second machine. The global optimization remains zero.
They just moved the patient into the waiting room faster.
Let's jump to the technology sector itself. The people building the tools.
We are in a modern software development environment. Agile sprints, stand-up meetings, continuous integration.
The developers here are now using advanced AI coding assistants.
They aren't just getting autocomplete, They are generating hundreds of lines of complex boilerplate code in a matter of seconds.
It's hailed as the ultimate productivity hack. The volume of code being produced per developer has skyrocketed.
The raw generation of code is incredibly fast. We have fundamentally altered the economics of writing software.
But generating code is only one lane on our metaphorical motorway.
Writing code is actually rarely the true bottleneck in modern enterprise software.
What happens when that mountain of AI-generated code needs to go to production?
In this specific organization, architecture reviews, security audits, and organizational compliance approvals still require manual sign-off.
From a senior committee that only meets once a month, and the senior engineers who have to review this code are now drowning in volume.
The code doesn't just sit there benignly. It's not like a stack of lumber waiting to be used.
Exactly. I mean, it sits in a queue waiting for human review. It's exactly like the cars waiting at the merge.
The developers are producing code 10 times faster, but the architecture board hasn't changed its meeting cadence.
And the senior reviewers haven't gained superhuman reading speed, so the system throughput remains completely locked to the speed of the approval committee.
And software inventory rots. While that code sits in the queue for a month, the underlying APIs change.
Business requirements shift and merge conflicts arise with other branches.
By generating code faster than the constraint could process it, the AI actually introduced system-level instability.
Let's look at one final example, and this one might be the most brutally stark illustration of the principle because it involves absolute physical space.
Imagine a massive global logistics hub, a warehouse the size of 3 football fields.
This company prides itself on being data-driven. They have implemented a cutting-edge, machine learning predictive model for their supply chain.
It factors in live weather data across the country, real-time traffic density driver, hours of service regulations, and historical delay patterns.
It predicts truck arrivals at the facility with astonishing pinpoint accuracy. It knows exactly when a trailer will cross the geofence.
It is a triumph of predictive analytics. It removes all uncertainty from the arrival schedule.
But then the physical hammer drops. The trucks arrive precisely when the AI predicted they would.
And then they park. And they sit idling in the yard for 4, 5, sometimes 6 hours.
Why? Because the facility only has 6 physical dock doors, 6 physical holes in the side of the building.
There are only 6 places where a truck can physically back up and be unloaded by a forklift.
The AI perfectly optimized the information flow. It optimized the arrival timing, but physics declined the software update.
You cannot digitally optimize your way out of a strict physical constraint. 6 doors is 6 doors.
If it takes 1 hour to unload a truck, the absolute maximum throughput of that facility is 6 trucks per hour.
It does not matter if your AI can predict the arrival of 50 trucks down to the second. 44 of them are going to sit in the yard.
Looking at the physics of it across these examples is incredibly revealing.
We just jumped across manufacturing, healthcare, software development, and global logistics.
4 completely different industries governed by different business models, employing completely different types of workers.
But they all share the exact same systemic engineering failure.
They are all mistaking a busy system for a productive system.
They are optimizing local KPIs, machine cycle speed, charting speed coding, speed predictive accuracy.
While completely harming or at least willfully ignoring global throughput.
That is the defining pattern of the current technological era, and it raises an uncomfortable but important question.
Why do incredibly smart, highly educated people working in well-funded organizations keep making this exact same mistake?
Why do we keep spending millions of dollars to widen the highway right before the traffic jam?
The dossier devotes a significant amount of text to answering this, and it comes down to human psychology.
It argues that optimization, particularly digital optimization, is deeply addictive.
Think about the dopamine hit of a modern software dashboard. When a management team implements a new AI tool and suddenly the dashboard goes from yellow to a brilliant green,
The charts climb up and to the right, and local cycle times shrink on paper. Everyone in the office feels incredibly busy.
and to the human brain, busy feels like important. Busy feels like progress.
We are biologically and culturally wired to celebrate visible activity.
Yeah.
We reward the person sweating and swinging the hammer fast, even if they are hitting the wrong nail.
But this is where the mindset of an experienced systems engineer is fundamentally different from standard corporate management.
When an entire department is popping champagne because they achieved a 30% reduction in time to draft a document using a large language model.
The experienced engineer is standing in the back of the room, quietly looking at the end-to-end data and asking 2 very uncomfortable questions.
First, compared to what? And second, did the system actually move?
Did the system actually move? Meaning, did the finished goods rate change at the shipping bay?
Did the patient get healed and discharged faster? Did the compiled software actually reach the customer and generate revenue?
Did the cargo get unloaded and put on the store shelf?
Right, because dashboards, by their very nature, almost always measure activity. They measure utilization.
They measure how fast the individual gears are spinning in isolation.
Engineers, specifically restorative engineers, do not care about activity. They look strictly for throughput.
They look for how much actual realized value exits the end of the system.
Activity and throughput occasionally intersect, but they are absolutely not the same thing.
In a poorly designed system, high activity is actually a symptom of systemic failure.
To really cement this idea, to burn it into the listener's memory, the FNROS version 2.0 dossier included this incredible visual metaphor.
It's written almost like a descriptive script for an installation at an industrial design museum. I want to walk through this slowly.
Because it perfectly encapsulates everything we've discussed. I want you, the listener, to visualize this space.
Imagine a completely flawless, beautifully engineered conveyor belt sitting in the middle of a stark white room.
It looks like it was designed by Dieter Rams, or the Apple Industrial Design Team. It is constructed of brushed aluminum.
Illuminated by warm, precise white lighting. The machining is perfect. There are no exposed wires.
It is the physical embodiment of pristine, localized efficiency.
It is what every tech startup promises to build for your workflow. You can imagine the pristine rhythmic sound of a single servo motor turning.
It's a gentle, impossibly precise hum.
And traveling down this beautiful, frictionless conveyor belt is a flawlessly machined, solid aluminum cube.
It is moving smoothly, quickly, and efficiently down the line.
But then the exhibit forces you to look at the end of the line. The camera, so to speak, pans down the length of the conveyor.
At the very end of this perfect high-speed conveyor belt is an industrial safety gate.
And it's completely solidly closed. It's a thick piece of unyielding metal.
The beautiful aluminum cube travels all the way down. The perfect conveyor at maximum optimized speed hits the closed gate and stops dead.
And because the conveyor belt beneath it is still running, still perfectly optimized, the cube just sits there.
And every few seconds, as the belt slips under it, the cube politely bumps against the gate.
Clink, wait, clink.
Wait, it's almost apologetic. It highlights the absurdity of the mechanism.
It is absurd, but the absolute punchline of this visual, the detail that makes it a brilliant critique of modern management.
Is that right next to this sad little cube bumping against the gate? There is a pristine, minimalist digital dashboard mounted on a brushed steel pole.
And the dashboard pulling real-time telemetry from the servo motor simply reads efficiency 99.9%.
If we connect this to the bigger picture, to the millions of dollars being spent on enterprise AI right now, this visual metaphor is the entirety of the problem.
That conveyor belt is not broken. It is working exactly as it was mathematically engineered to work.
The motor is flawless. The KPI on the dashboard is technically mathematically true.
The task of moving the cube from point A to point B is incredibly efficient.
But it is beautifully engineered waste. The system as a whole is doing absolutely nothing useful.
The cube is trapped. The objective hasn't been met. It's doing nothing useful, but it looks fantastic doing it.
The metrics assure everyone that a great job is being done, which is the most dangerous kind of failure in an organization.
Because it actively disguises itself as success. You don't fix what looks like it's working perfectly.
You don't investigate the green dashboard. You only investigate the red ones.
And if the constraint doesn't have a dashboard, it remains invisible while the rest of the system optimizes itself into a state of paralysis.
So how do we fix it? We've diagnosed the disease. How do we solve the root cause?
The dossier continues this visual metaphor, turning it from a static exhibit into a story of active intervention.
And this is where we get into the core concept of restorative engineering.
So continuing the scene in our minds, we have the running conveyor, the closed gate, the bumping cube, the 99.9% green dashboard.
And then a human engineer walks into the frame.
And what does the engineer do? This is the most crucial part of the sequence. They completely ignore the efficient conveyor belt.
They don't even glance at the dashboard. They don't check the telemetry of the servo motor.
They don't attempt to write a new prompt to optimize the speed of the belt.
Because the engineer knows, through training and tacit knowledge, that the speed of the belt is just a symptom.
It's a localized variable. They walk past the safety gate. They move downstream.
And they investigate the physical workstation that is situated after the gate.
And what they find is the actual truth of the system. The downstream workstation is completely physically full.
It is overflowing with finished products that haven't been cleared away.
There is physically nowhere for our little aluminum cube to go, even if the safety gate were to open.
The system isn't jammed at the gate. The gate is just a protective mechanism. The system is blocked by a lack of capacity downstream.
This is the moment of restoration. This is what systems engineering actually looks like.
The engineer doesn't write new code. They simply reach out and they remove one finished product from that downstream workstation.
They physically clear a single unit of capacity. And automatically, because mechanical systems are connected through feedback loops, the safety gate recognizes the newly opened space.
The gate drops. The aluminum cube smoothly moves through and into the workstation.
Think deeply about what just happened in that sequence. The conveyor belt itself never changed.
If speed wasn't optimized, its software was never updated, no new generative AI was deployed to the motor.
But suddenly, the entire system flows. The throughput of the system was instantly restored simply by understanding where the actual physical constraint lived.
Then addressing it directly. This raises an incredibly profound point about why humans still matter in this loop.
We get so caught up in the cultural narrative that AI is going to universally replace human intelligence.
That algorithms will manage our factories and our workflows flawlessly. But an AI agent living inside a server cannot quietly walk through a physical factory floor.
It can't notice that the maintenance team looks exhausted, understaffed, and demoralized.
An AI cannot read the subtle social dynamics of a corporate office and sense that a rigid, fear-based approval culture is delaying product launches.
Regardless of how fast the raw code is written, that is the boundary of artificial intelligence.
AI has absolutely no instinct for hidden constraints. It possesses no out-of-band perception.
It has no context outside of its specific training data and its immediate localized objective function.
It cannot step back, look at the bumping aluminum cube, and ask the philosophical question, wait, why are we even moving this cube in the first place?
So what does this all mean for us in a world where we are rapidly approaching an era of infinite AI acceleration?
Where generating text-writing code, drafting legal arguments, and scheduling logistics will be virtually free and nearly instantaneous.
What is the actual enduring job of the human being in the system?
The job of the human shifts fundamentally from execution to direction. For the last 100 years, humans were the engines of execution.
Now the AI is the engine, the human is the navigator.
The human is uniquely responsible for choosing the objective. The human is responsible for understanding the true overarching purpose of the system.
We have to be the ones who possess the critical thinking to question the metrics on the dashboard when they don't align with reality.
We have to recognize the unintended consequences of moving too fast in the wrong direction.
Technology, whether it is a physical conveyor belt from the 1950s or a state-of-the-art large language model, merely accelerates execution.
Engineering, which is a profoundly human endeavor involving judgment, ethics, and physical reality, determines the direction.
The greatest responsibility we have right now isn't building faster systems.
It's understanding our systems intimately enough to know exactly where speed actually matters.
We have to be the ones who find the gate.
We must identify the constraint, because accelerating anything other than the constraint is just generating heat.
It is just adding friction and noise to a system that desperately needs flow.
I want to speak directly to you, the listener, right now. I want you to take a mental step back from whatever you're doing today.
Look at your own daily work. Look at your team's workflow. Look at the software tools you use.
Especially the new AI platforms your company is so eagerly rolling out this quarter. Think about the projects that are taking up all your cognitive bandwidth.
And I want to pose that master question to you one last time. It's a question you should probably write on a piece of tape and stick to the bottom of your monitor.
If your current project became 10 times faster tomorrow, would your organization actually improve?
Or would you just be rushing toward a closed gate?
It is a confronting question. It forces you to look past the illusion of your own productivity.
But it is a necessary one. Because reality always gets the final vote. You can have all the green dashboards in the world.
You can have the most beautifully optimized AI executing your tasks. But if the global throughput of the system doesn't increase, reality wins.
Good engineering, and frankly good leadership, is simply learning to listen to reality earlier in the process.
It is learning to observe the physics of the system before you try to write code to fix it.
Everything else is just motion dressed up as progress.
Before we wrap up this deep dive, the dossier leaves us with one final, deeply provocative synthesis.
And it's an economic reality that I haven't stopped thinking about since I read the final pages of the FNROS version 2.0 text.
We are entering an era where everyone's going to have access to this baseline AI acceleration.
The cost of execution isn't just dropping for you and your team, it is going to drop to zero for your competitors too.
That is the critical strategic insight that most businesses are entirely missing while they scramble to adopt AI.
When every single company in the world can write boilerplate code, generate marketing copy draft contracts, and optimize schedules at light speed.
Speed itself is no longer a competitive advantage. It ceases to be a differentiator. It simply becomes table stakes.
So if speed is entirely commoditized, if execution is essentially free, who wins?
The only organizations that will survive, let alone thrive in that environment, are the ones that have retained the human tacit knowledge required to accurately identify the bottleneck.
In the future, the highest paid, most valuable skill in the marketplace will not be writing the perfect AI prompt.
It won't be managing the AI's output. The most valuable skill in the world will be finding the constraint.
Because the company that points its infinite zero-cost AI acceleration at the right constraint will effortlessly outmaneuver the company that points its AI at everything.
Finding the constraint. It's not glamorous work.
It means walking past the green dashboards. It means looking at the messy physical realities of downstream workstations.
It probably won't trend on social media.
Yeah.
But looking at the physics of it, that is the only place where real progress is actually made.
Thank you for joining us on this deep dive into the Field Notes dossier. We'll leave you to think about where your bottlenecks are hiding.
Take a very close look at those dashboards.